To calculate the RMS, the root mean square value, I'm just going to proceed through the slides at this point. I want to make sure we finish. We will eventually answer the question I just asked. Why would we need to do this? What's the average value of a sinusoid?
Zero.
Zero. Asking for the average potential difference across the resistor, we're going to get zero. We're going to get zero. Asking for the average current, we're going to get zero. Asking for the average power, we're going to get zero. So how do we fix that? Well, we calculate the root mean square. Square the current so that it is positive, then take the average of that, and then take the square root of the result so that we're back into the neighborhood of current. And this horizontal purple line right here represents the root mean square current. Where did the square roots of 2 come from? We took the current, we squared it. We found the average, but the average of cosine squared is a half. Over a period, if we find the average value of cosine squared, it's equal to 1/2. So the average is half I squared. We took the square root again. Okay, that's I squared square root, that's I, but now we've got that factor of 2 in the denominator that we took the square root of. If we want to calculate the actual power, the average power supplied or dissipated, we can multiply the RMS current times the RMS voltage. When a resistor is connected across an AC source, everything's fantastic. The current varies, the potential varies, the resistance is constant. Fantastic. Current and voltage through and across a resistor are in phase. Nothing new here. If we represent it as a phasor, the current and the voltage through and across the resistor are in phase. They're parallel as far as phasors are concerned. They have the same orientation. I don't understand. Why? I mean, I guess you're just telling me. We knew this. We knew that they were out of phase. And we know that they have this relationship. The phasors are 90 degrees apart. We knew that. Where does what why? Why? And for that matter, why? Here we are trying to answer the frequency dependence. Where does this omega come from? Here again, the current and the voltage through and across the resistor or the capacitor are out of phase. The phasors have different orientations. The orientation between them is preserved as the whole apparatus rotates in the imaginary, like in the augmented complex plane. This is a cool plot. What are we showing here? This is three different the resistance and the, what is this called? Reactance. Okay. The resistance and reactance. Resistance is constant. Great. If the reactance of a capacitor is 1 over the capacitance and also 1 over the angular frequency, it should decrease as frequency increases. The reactance of an inductor, just omega L, should increase linearly as omega increases. Okay. If omega is 0, which is a DC circuit, there is no current through a capacitor. Wait, what? In the steady state. The initial transient response where everything adjusts and finds its equilibrium, okay, but there is no current through a capacitor because, well, its reactance has become infinite. It's become charged. In the steady state. Gosh, that looks really familiar. I feel like this isn't going to make sense until I figure out where those reactances came from. But I suppose once we take those for granted, this makes a certain amount of sense. If we multiply this expression by the current I, the I times the square root, we can push the I through the square root if we square it. So then we have I squared distributed into the radicand. But I squared R squared is the potential difference across the resistor squared, which was the first term for our voltage across the source. So that makes sense, I guess. And if we push the I, if we distribute it into this as well, maybe we get to unpack we get to talk about convert reactance back to potential, and we can say what we just said about the potential difference across the source. So here we're expressing it in terms of the units of resistance, I suppose. We just wrote a thing talking about the source that has the units of volts, but if we pull out the current, we should end up with something like ohms, and I guess that's this. Capacitor, inductor, resistor, 3-vector sum. They've got phi, we have alpha in our notes. If the capacitor dominates, then the angle could be negative clockwise. And the response in the resistor has its maximum before the response from the source. The source voltage lags the current. Is behind. Instantaneous power is always positive because the current and the voltage are in phase. If one of them is negative, so is the other one. So the product will always be positive. Sometimes through an inductor and a capacitor. The current and voltage have the same sign. Sometimes they have opposite signs. The power is positive when they have the same sign, negative when they have opposite signs, and the average power is 0. They are not dissipative elements, they are storage elements, frankly. Average power is positive, and here's our relationship for it. We're going to find it with the RMS voltage, current, and there again, that cosine of the phase angle between the current and the voltage, called the power factor. If impedance, which is different from reactance, which is different from resistance, if impedance, even though they all have the same units, if impedance is minimized, then we can have the largest possible response, which happens when the reactances of the inductor and the capacitor are equal, so that that term in the radicand becomes 0, and because that's as small as we can make it, because it's squared, we're not going to be able to make it negative. That's the same resonant frequency as an undamped LC circuit. And this helps explain the response of the animation. When we change the resistor, the shape of the curve changed, but it didn't change the location of resonance. Resonance just means that the two inductances, I'm sorry, not inductance, so many words, that the two reactances are equal. Never mind what the resistor's doing. The lower the resistance, the stronger the peak. We saw that. Yep. And we have two slides talking about transformers. I'm going to save transformers for Tuesday. Actually, I'm looking at the clock and I'm thinking about what we have to talk about. I'm going to save because it's a nice sort of catch up. It reminds us of some things we talked about earlier, in especially in the DC circuits, and sort of it lets us sort of marry DC circuits and AC circuits in a nice way. They're different, obviously, but there are some ideas that we might have talked about in the DC circuits sort of topic that I said I wanted to wait on, and that actually there's another thing that we could go back and visit, which was a discussion of back EMF in a DC motor. Back EMF at the time just sounded like hocus pocus. As well, it's a thing that they told us happens and it's not really clear why. But now that we have induction, we can talk about why. The back EMF is just the induced EMF. And we can actually talk about what happens when a drill bit gets stuck, and that back EMFs can really be a problem, and then you can overheat your motor and the windings can melt, and it's a problem. So we can sort of grab those two applications on Tuesday. Before we're done today, I want to finish the story of these reactances. Where the hell where did they come from? What is this? Why? The nice thing about it is that it's a relatively short story. We knew this already. That the potential difference, the induced EMF across an inductor, is proportional to its inductance and the rate of change of the current. But we know the current response now. It's I0 cosine omega t. So wait a minute. I think we can do better than that. Because we have our augmented reality goggles. At any given time, the actual measured potential across the inductor should be the real part of V sub L sub 0 e to the j omega t. It should also be equal to the real part of the inductance times the current. Yeah. Now the current, let's see, the potential across the resistor as a function of time was the real part of VR0. The current through the circuit at any given time is the voltage divided by the resistance. So what is the derivative of the current? I'm just going to call it I. The complex current has a magnitude, and when we take the derivative of e to the j omega t, we get a factor of j omega. V sub L sub 0 was the magnitude of the inductor voltage times e to the j theta times e to the j omega t. I don't know, the current might be, let me make sure we had R-E-L-I j omega t. All right. We've got an e to the j omega t on both sides. Let's get rid of that. The inductance is fully real. We can pull that outside the real operation. The current, however, the current should be the resistor voltage divided by the resistance. But the resistor voltage sort of phasor has an e to the stuff component, right? Let's see, the inductor leads, so that's plus pi over 2. The current is just, it's the current magnitude times e to the j omega, or I'm sorry, e to the j theta. That's the whatever the initial sort of, I suppose we could go with our original initial conditions and just say that the theta is 0 if we start from like uncharged capacitor, no current flowing. That would probably simplify the notation. Well, it's just 1. So we don't need that. But e to the j pi over 2, we know that value. It's j. Now we can take the real part because there's nothing complex left. We canceled it. And it looks like, if we compare this relationship to Ohm's law, that omega L has the units of ohms because amps times junk should be volts if junk is ohms. So this is some kind of resistive character of an inductance according to the angular frequency with which we try to drive it. Which does match our intuition. We were sort of chatting, looking at the animation, at the simulation earlier, saying that if we try to use a larger angular frequency, that the rate of change of current is going to be really high most of the time. And inductors don't like a high rate of change of current. They want to oppose that. So the faster we try to adjust the current back and forth, the more the inductor is going to try to stop us, the more it's going to feel like resistance, the more it reacts to us. We call it reactance. So why does the capacitor one look so different? That's pretty cool. There's a really neat symmetry there. We like symmetry. That means, well, we already wrote the potential across the capacitor. Where do we write that? Potential across the capacitor is the real part of V sub C sub 0 e to the j omega t. V sub C sub 0. All right. And the current is I e to the j omega t. No, wait a minute. The derivative of the potential. Hold on. The derivative of V sub C sub 0 e to the j omega t. But the derivative of that is j omega, right? We're going to get a factor of j omega. V sub C sub 0 was the amplitude times e to the j negative pi over 2, j omega e to the j omega t, I e to the j omega t. E to the j omega t cancels. E to the negative j pi over 2 is actually negative j, but negative j times j is just 1. So this is VC equals I. And what we have, we just left with C and omega. Again, this is a thing that needs to have the unit of ohms because it's occupying the normal spot for R in Ohm's law. So it talks about how apparently a capacitance opposes being driven with an angular frequency. The faster we try to alternate the current, the happier, the less like a resistance a capacitor feels, because it doesn't charge. If we start with it uncharged and we turn on the current a little bit in one direction, we move a little bit of charge. But that's at the point where it's still easy to store charge on the plates because there's no existing field to oppose our putting more charge on the plates. But then by the time we stack a few charges on the plates, the current has already alternated and now it wants to move them off. But it's really easy to do that. It becomes harder if we allow the capacitor to charge or if the capacitor would charge more in the amount of time that it takes the current to alternate, which the time constant depends on R and C. And so if the capacitance is bigger, the time constant is bigger. So if we allow for more, if it would take more time for the capacitor to charge because we increase the capacitance, then a alternating current is able to charge the capacitor less on average, which means it behaves more like a wire. The more charge builds up, for a smaller capacitance, we charge it up really quickly. For a slow angular frequency, we have a lot of time to spend with a positive voltage charge in the capacitor. And the more we do that, the more it tries to resist our storing more, the more reactive it is. My favorite thing about this is that I just want to quickly I don't know. I think this is better. The textbook doesn't include the complex, well, this textbook, the Young and Friedman text, does not include the complex treatment with the AR goggles. But I think it's better, especially since we used the complex treatment last time. Questions, comments, concerns? We will, as I talked about, we will talk about transformers and back EMF on Tuesday. Study materials are going up tomorrow morning, probably. And on Tuesday, we'll discuss that as well. And hopefully spend a little bit of time talking about waves. Not electromagnetic waves, just waves. And that's my plan for Tuesday. And then we've got the test on Thursday. Thanks for your attention today. I appreciate it. Have a great night and a good weekend.
Hey, you too.
Thanks.